Welcome back. In the previous experiment, we saw how a potentiometer can be used to compare the EMF of two cells. Now we are going to see how the same potentiometer can be used to determine the internal resistance of a primary cell. It can be any cell, it can be a Lagrange cell, it can be a Daniell cell. So first let us go through the theory of the aim of the experiment is to determine internal resistance of a given primary cell using potentiometer. What apparatus will you require for this experiment? Of course, you require a potentiometer. You will require a battery eliminator which will act like your driver cell or power source. You require two one-way keys, and you require a rheostat which will be used for increasing or decreasing the resistance, which will help you control the current that will flow into the circuit. Then you require a galvanometer. Of course, it is a null deflection method, so a galvanometer will be useful. Then you have a high resistance box, one ammeter, one voltmeter. Of course, a cell whose internal resistance is to be calculated, and then the jockey. You require a scale or a set square, and of course some connecting wires along with a small sandpaper to ensure that there is clean connection. Okay. So let us first go into the theory part. Just to remind you that we have already seen that if you have a cell which is connected to some external resistance, and initially if the key is open and if you connect a device that can measure potential drop, then with the key open, whatever you find out or whatever reading is obtained, that is called the EMF of the cell. But the moment you close the key, a current starts to flow in the circuit, and instead you will see that the reading will be less than E, and I call that as the terminal potential difference. Why this happens? Why V, which is terminal potential difference, less than E? V is less than E because there is another resistance that comes into play when current flows through the cell, and that is your internal resistance. It is the resistance offered by the electrodes and electrolytes of the cell to the flow of electric current. How do we find out? Well, we had found out that internal resistance R is given by E minus V by V into capital R. So this is our working formula. The moment you have current flowing in the circuit, internal resistance comes into play. There is a potential drop I into R that takes place across the cell, and that is the difference. So V is E minus IR, and previously we have seen that I into R is called the lost potential. You are not able to use this potential. So if you are buying a battery of 9 volt, you are not able to get exactly 9 volt output, to get something less. And this internal resistance depends on various factors. It depends on the plate area, how much area is immersed into the electrolyte, temperature, nature of electrolyte, and so many other things. So how do I use a potentiometer to determine this internal resistance? So for this, we go back to the auxiliary circuit of potentiometer. Let us do that. Let us go back to the circuit. So let me just have my working formula here, E minus V by V into R. That is my working formula. How am I going to use it? Here, let's see. So let us look at the auxiliary circuit. We have the driver cell, then the rheostat, ammeter, key, so instead of those 4 or 5 wires, I just have only one single wire that is connected, and the point where the jockey will touch the wire will be the contact point. The galvanometer is connected. So you can see there is a gap. So how do I determine the internal resistance? So what I will do is I will connect my circuit here. Suppose I call my K prime, and this is my external resistor R, and suppose this cell has EMF, suppose I call that as E prime. This EMF, this driver cell has EMF E, this cell has EMF E prime. And remember, E prime has to be less than E for the circuit to be able to determine the balance point. Otherwise, balance point will go or not go. Okay. So how do we proceed? Step 1. Keeping K prime open, obtain balance point, say at J1. Suppose you have this K prime open, so no current is going to it. Then you slide the jockey and suppose you obtain the balance point at say J1. Now remember, potential drop AJ1 will be proportional to length L1. So this is L1 is the balancing length. This is where the galvanometer does not show any deflection. So that will mean VAJ1 will be equal to some constant K into L1. Let this be equation 1. Then I apply Kirchhoff's rule, the loop law. So by KVL, Kirchhoff's voltage law, what do I get? Again, look back. If I look at the loop A, J1, galvanometer through the cell E prime and back to A. If I see, this is one complete loop. And in this loop, you can see that only potential drop that is taking place is A to J1. So only potential drop is VAJ1. But what is the only EMF in the circuit? E prime. So by KVL, VAJ1 is equal to E prime. So this essentially means E prime is KL1. Let this be equation 2. Fine. Now go to step 2. In step 2, close K prime. When you close K prime, you will see that the balance point is again disturbed. The galvanometer will show some deflection. Why? Because once you close K prime, there is a current that will flow here in this circuit. So the balance point is disturbed. So then what do? You try again searching for the balance point. You slide the jockey on the wire and suppose you obtain the balance point at J2. Suppose at a length L2. Now why should you expect the balancing length to be less? Because now what is the potential difference that you are finding out? It is not the EMF, it is the terminal potential difference, and terminal potential difference is always less than the EMF. So you expect a smaller balancing length or a shorter length at which the galvanometer will show zero deflection. So close K prime and obtain balance point, say at J2. Then by principle of potentiometer, VAJ2 is proportional to L2 or VAJ2 will be equal to K into L2. Let this be equation 3. Now we all know by KVL, VAJ2 should be equal to what? Be careful. Now there is a current flowing in through the battery. So when a current is flowing through the battery, when the circuit is closed, the potential difference is not EMF, it's the terminal potential difference. So instead of E prime, I will write it as V, which is the terminal potential difference. So that essentially means V is equal to KL2. Now let us go back to the formula, the working formula for R. So when you look at the working formula for R is equal to E minus V by V into R. So here the E is E prime, this cell E prime. So R can now be written as E prime can be written as KL1 V can be written as KL2, V is again written as KL2 into R. So K gets cancelled throughout. So small r is L1 minus L2 by L2 into R. So this is the final working formula, and this is how we can determine the internal resistance just by calculating or knowing the balancing lengths when K prime is open and when K prime is closed. So for the detailed experiment, we will go over to ma'am who will explain how the internal resistance can be obtained with proper precautions. And of course, after the experiment, you have to look at the observation table. You have to have a milliampere reading. Then, without shunt, basically this resistance, this R is called a shunt. Without the shunt, and with the shunt, and then you find out that
Welcome back, children. I am going to explain the experimental arrangement of quick experiment, that is internal resistance of the cell using potentiometer. Already the circuit diagram is here. As it is given in the board, 0 is connected to positive of the battery, ammeter, resistor, second row. Here this diagram is mentioned 400 cm. But actually we have 10 wires on the potentiometer, each one of 1 meter length. So total length is 1000 cm, not 400. Like this, 4 wires, 10 wires are in series. So it is 1000 cm. Now, come to that circuit connection. 0 unit of the potentiometer is connected to positive or negative meter. There will be millimeter, rheostat, then other end of the potentiometer. Again, same 0 unit of the potentiometer is connected to positive of the reflector. Keep in mind, all positives, maybe of cell or battery, all of them connected to the same point. That is 0 unit of the potentiometer. Now, Leakland cell, as it is a Leakland cell, this is carbon dot positive electrode, zinc negative, and a sound resistance is connected parallel to the cell with the help of a one-way key. Positive end is connected to a sound resistance of small resistances are there, that is connected to key to negative. So this is a parallel connection, a sound resistance is connected parallel to this. Then negative terminal of the negative electrode, that is zinc rod, is connected to one-way key, then to galvanometer, high resistance box, and finally to junction. This is your circuit connection, and always you keep in mind that EMF of driving cell, that is battery elementer, should be more than that of the cell used, that is the Leakland cell. And as you have done in previous experiment, we are using a voltmeter. Initially we will check the EMF of the Leakland cell. Now connect the positive of the voltmeter, connect to positive, and everything is switched off. Connect it to positive and negative to negative. It shows around 1.4 volts. So EMF of Leakland cell is now 1.41. Battery limiter is set at 2 volt. The voltmeter which is used, it has a range of 2 volt. Least count of the voltmeter is 0.05 volt, because 0.5 volt is divided to 10 divisions. So least count is 0.05 volt. Similarly, the milliammeter which is used here has a range of 500 milliampere, and 100 milliampere is divided to 10 divisions. So least count of the milliameter is 10 milliampere. Now to start with, note down. We will note down the current in milliampere. The current shown is here 20 milliampere. So here we mention current in milliampere and millimeter 20 milliampere. Then we have to find position of ground points. First, without shunt. Without shunt means the shunt resistance is not connected, and always check all these keys are tightly closed. It is not loose. All the keys are tightly closed. Before doing the experiment also, you will check all the connections should be tight. Okay. If there is if it is loose slightly, sometimes the galvanometer will not set, it may goes and defecting. Check all these keys. And then first we will get without sound. Without sound means we will keep the sound key open. Without sound. Sound key open. Now the sound resistance is not in connection. Then we have to take without 2000 ohm. Without taking any resistance from the resistance box, we have to find the balancing line. Balancing line, as you have done in previous experiment, you will check like that. Go on touching, starting from the first layer, right deflection, second right, third right, fourth. Likewise, go on checking, and here again on the 8th layer we are finding it shows left deflection. That means on 7th layer it shows right deflection, on the 8th layer it shows left deflection. That means normal deflection is between 7th and 8th layer. So we have to check only 7th and 8th layer. We go on checking along the 7th layer. Then 8th layer is connected in series with this metal piece. We come to 8th layer. 8th layer. Here the galvanometer shows, pointer shows 0 deflection. Pointer is at 0. So now on 8th layer, as the deflection is coming, 0 deflection is coming, we have to measure the length L1 without shunt. So use a scale. 8th layer means 700 complete plus something. So 700 completed. After 700, you start using this scale, upper scale, and it is around 740. So without taking any resistance, balancing length L1 is 740. So you will mention here 740. Now with 2000 ohm. So you will take 2000 ohm. Now as you have removed, current passes through the, here there is a gap left. Current cannot pass through this metal block as the path is open here. So it will pass through 2000 ohm resistance. That means 2000 ohm comes into play. And you have to find the balancing. Almost it will come nearby. It is not coming on the 7th layer. It is coming on the 8th layer again. Around 800, 751. 751. So you say around 741, it is 751, then find the mean. So got the balancing length L1. Now balancing length L2 with shunt. L2 is balancing length with shunt. Replace the 2000 ohm key here. Bring the shunt resistance into connection. And to some shunt resistance, let it be 0.5 ohm. So suppose I take out the shunt resistance of 0.5 ohm. So in the last but one column, here you will mention shunt resistance 0.5 ohm. And you will find the balancing length. Like previous one. Now the balancing length is coming to me. Suppose it is coming on the 3rd layer now. It is coming on the 3rd layer. 3rd layer, that means 200 plus. 200 ends here. 200 plus means upper scale you will use 236.2. 236.2 is the balancing length with sound. Then again with 2000 ohm. Here it comes around 256.5. So we mentioned here it comes between 200 to 300 without shunt, without 2000 ohm, without shunt and with 2000 ohm. Both these things it comes between 200 to 300 we will mention here. Then find the mean. Then Already you have mentioned sound resistance. Then calculate the internal resistance using the formula. It is the value L1, L2 and I. Find the sound resistance. Then take out the key. Let the current comes back to previous one. Again set it. Keep the sound key open so that sound resistance is not in connection now. It was left open. Then there is the current key, and again you start taking observation. Follow the similar process. Balancing length L1 without sound. That means without 2000 ohm, with 2000 ohm. With 2000 ohm means you will remove this key. So it is with 2000. Without means without taking out any key. All these are in connection, so no resistance is happening. It is without 2000 ohm. Take twice and the mean. Then we come to with sound. Balancing and with sound means always put the sound key so that this resistance comes into play. Then apply some sound resistance maybe 0.5 plus 0.1, 0.6 and for the balancing length. Again get 2 without 2000 ohm, with 2000 ohm. Find the mean. You substitute all the values, calculate the internal resistance. Like this you take 6 observations, minimum 6 observations, then find the mean internal resistance. That's all about this experiment. And precautions as I have told you earlier are almost the same. And while starting, always we will check whether once the connection is done, always we will check on the first wire and the last wire. If it shows both sides equation, then the connection is correct. Otherwise, you have to check whether everything is wrong. And almost same precautions that everything should be tightly closed. The keys of the resistance box to be tightly closed. Don't rub it or place it hard on the wire. Move it gently, and only you put the key whenever necessary. Whenever you are taking observation, put the key. Don't allow current to pass unnecessarily for a longer time. And the driving cell should have more EMF than that of the cell. These are all the precautions for this experiment. Next, we will start the 6th experiment. It will be explained by Sir. We will again come back to